Okay, so I have remembered we are going to start off with the thing that I had forgotten to tell you earlier. So I did put the notes for this earlier. Actually, I can just swap to them now. Actually, I guess I don't have to do this yet. There are 3 molecular orbitals that we're going to deal with that actually are a bit different that I had neglected to mention earlier. I had forgotten. Whoops. So for the elements, for boron, carbon, and nitrogen, you're going to want to use a molecular orbital that looks like this for your P's. So it turns out that these two are going to be swapped from where they normally are in the rest of ours that we've seen before. So mostly we focused on oxygen and fluorine last time. We did do nitrogen as well, but I had forgotten to switch these two. You get the same result. You still get a bond order of 3 and everything. But when you're dealing with like random ions like N22 plus or something, that can have an effect on whether it's going to be paramagnetic or diamagnetic. I don't want you to get anything wrong on your homework or in the future. So I have to address this. So my bad, I guess, would be the answer there. So just don't forget, if you have one of these 3 elements there, you're going to want to swap your pi 2p and your sigma 2p. Normally, remember, we have our other ones that have sigma as the lowest, and then we go to pi star, sigma star. And that's going to be for your later elements on that. So we go to the normal one at oxygen and further. Okay, so that's just something to keep in mind for your homework. So I can just drop this in your lecture notes. I put it somewhere in like the general thing, but let's put it in lecture notes just in case. Okay, so that'll be there for your homework when you're working on that. Okay then, cool. Back to gases then. Alrighty. So we know that we had the unit of millimeter of mercury for pressure. Let's go ahead and take a moment to look at that. We'll show you some devices that actually use this unit, and we can then use it in some calculations. So millimeters of mercury at glance, is this a unit of distance? Like you might think, because it's got millimeters in it, right? We have this archaic device, no longer something that is really used. We have more fancy ways now to measure pressure. But way back when, you would have a device like this. This is mercury, which is a liquid. It's a very dense liquid too, so it's extremely heavy for its volume. And so you'd have this tube that had a vacuum inside it at the top. And you would see that the atmospheric pressure would be pushing down on this mercury, as the atmosphere does on everything. And it actually will force some of the mercury into the tube here. And so the mercury is forced against gravity into the tube. So if you're pushing down on it, that mercury has to go somewhere. So it says, well, you know what? Hey, there's this area up in this tube that has no pressure. There's nothing pushing down on me inside this tube. I'm going to go up there. And so the mercury will travel up the tube. This is called a barometer, by the way. And so it forces the liquid up into the tube. And it turns out that the height of that liquid at 1 atmosphere of pressure would be 760 millimeters. So you can imagine 760 millimeters is about, what, like 2 1/3 feet or something? If you want to think about it in US units. I don't know, it's something like this, maybe, for what that's worth. So the mercury would rise up in that vacuum tube against gravity up to that level. And so that's how they would actually measure atmospheric pressure previously. And so you would look at the height of the mercury in that column. So basically how much the pressure can force the mercury up the tube before gravity says, you know what, no more of this. And so it's kind of where that fight is, where it resolves, is where your pressure would be read at. And so they had determined that 760 millimeters was 1 atmosphere of pressure. So it's just an average about 760 millimeters of mercury in the height of how far the mercury would travel up the tube would be how they'd get that. And so they actually had done this with various gases as well. So this is for measuring atmospheric pressure, right? So the atmospheric pressure pushes down, forces mercury up in the tube. The height of the mercury in the tube is your pressure. There's another device called a manometer, which compares two pressures. So you would have, let's see if I can draw nicely. Yes. You would have your gas in this vessel, whatever it happens to be. And you would have your mercury would be in this kind of tube here. And so your gas, the pressure of your gas, would push down on that mercury. And you could either have a second gas, but more likely you would have this open to the atmosphere. And you would therefore have your atmospheric pressure pushing down on the gas in that side of the tube. So you would see that you would have your gas sample, whatever that happened to be, pushing down on your mercury. You'd have your atmospheric pressure pushing down on your mercury. And you would see that mercury level would adjust such that the pressures would be, canceling each other out. And so the difference in the heights of those two, change in pressure, or let's just say it's the pressure of the height of the mercury. You would see that your gas pressure would be equal to your atmospheric pressure plus whatever the change in height would be. Let's just say delta H. That would be, I think, the but no, I want to keep this in pressure. So, for example, if this were 100 millimeters, that height difference, you would say, okay, your gas, let's say this was done at sea level, would be 760 millimeters plus 100 millimeters of mercury. And lo and behold, you get the magic number of 860 millimeters of mercury. So your gas is exerting a bit more pressure in this case. It could be the opposite. If you had your gas that was exerting less pressure in your manometer, if this were the case, you would be looking at the difference the opposite way. You would be looking and saying, okay, your P of your gas, whatever it is your atmosphere minus the height of that, or the difference in height of those two levels. If your gas is of lower pressure, you'd be able to make that determination, by the way, which one is lower, by looking at the manometer itself. So if you notice the side of your atmosphere was taller, that means your gas has higher pressure, your sample. If the side of your sample is higher, that means that you have less pressure than the atmosphere. And so you'd be able to kind of measure it in this manner. So this is how people used to measure gas pressure. Nowadays, there's all sorts of fancy electronics that do it for us that I don't understand, because I don't understand electronics at all. I'm terrible at circuit diagrams and all that stuff. Physics was not my favorite going back to chemistry, or back to college. So I have no idea how they work, but we have digital ones now, so we don't need these anymore. And of course, mercury is terribly toxic and all that sort of thing, environmentally hazardous as well. So it's good that we don't have to use these anymore. So if we say this is 100 millimeters again, we could say the pressure of the gas is 760, or whatever your pressure is. So that would be given to you, minus 100 millimeters. And so that would now be, we have 660 as our pressure. I don't even know what I'm doing with sig figs. Yikes, shame on me. Wow, look at this. I'm just copying things wrong. Yikes. Alrighty, so that is how we used to measure pressure. But it's always fun to torment students by giving them problems like this. Let's go ahead and take a look at a problem involving something like this. Oh, the other way. Okay, we're actually going to have an example. So let's say this is let's say we have, I don't know, a volume of 0.625 liters. And what gas do we want? How about we do chlorine gas? So we're going to say we have chlorine gas in this chamber here. Let's see if we can figure out how many grams of chlorine we have in this this sample container here. So, and let's say this is at sea level. We've gone out to the beach and we're doing our experiment with chlorine gas. Because why not? That's always a fun thing to do. So let's go ahead and we're going to bring our mercury and our chlorine to the ocean. That seems like a real smart idea, but it'll make our calculations a little bit easier. Yeah, typical beach day, exactly. It's Memorial Day weekend, let's just go out and do our gas experiments. Okay, how the heck are we going to approach this? So keep in mind, we have essentially two formulas for this chapter, so far at least. We have the ideal gas law, which we would use to solve for one of our four quantities if we had three of the others. And then we have the combined gas law, which would be for when we have things changing here. So of those two equations, which one do we think we're going to be using? Do we see a... Yeah, Kevin's got the right idea. Yeah, we should be using the ideal gas law here. We don't have things that are changing, it looks like, in this case, so that tells us we should be using the ideal gas law. So with that in mind, now let's see what the heck we do have with this. So with this, it does look like we have... I see right here we have a temperature and a volume. We're okay there. And of course we have R. R is just a constant. So we have two parts that are missing from this right away. But the other piece of information we do have is that we do have something about the pressure here. So we could figure out the pressure as well, which tells us we're going to be solving for moles. And since we're asked to calculate grams, that makes sense, right? Once we have moles, we can then apply that to figure out what the grams are going to be using our molar mass. So, with that in mind, let's see what the heck all these variables are going to be. So the pressure of the gas, in this case, is our gas pressure higher or lower than atmospheric pressure? Yeah, our gas pressure is higher, right? It's pushing down on that mercury more. It's got a stronger force. So that tells us we're going to be adding our height of our tube with plus the atmospheric pressure. So that would be 760 plus, let's put 760.0 for our sig figs. We're right at sea level on the perfect day, which tells us we have 984.1 millimeters of mercury is our pressure of our gas. However, we can't use this, right? Can we use millimeters of mercury in our ideal gas law? Nope. Combined gas law, yes, go ahead, but not in ideal. Ideal, we must use atmospheres. So how the heck do we convert this again? What's the magic number? Yes, indeed. 760 is going to be our conversion factor. Kevin will do that for us. In the meantime, we can also adjust our temperature, right? That's in Celsius. That's not a good idea. Why the heck do we have a gas container of 200 degrees at the beach? we're just having so much fun. So that's 473.15 Kelvin. Great, thank you, Kevin. Okay, now we finally have enough information to plug into our gas law. So, solving this, of course, N equals PV over RT. So that'll be 1.29 atmospheres. We had our volume that was given to us. R, and then of course our temperature. So let's just make sure we get moles out. Always double check. Liters cancel, kelvins cancel. Yeah, we're left with moles. Thank you, Kevin. Wow, that's really not that much. Oh, I guess it's pretty high temperature, huh? Alrighty. Are we done? No, not quite, because we were asked in the question how many grams of chlorine do we have. So far we have not needed to use the information that this was chlorine gas. Remember, all gases behave the same way according to our assumptions. So if we wanted to convert this guy into moles, we would have to use our molar mass. And we'll have that answer shortly. Very nice. Sig figs look okay. I think we should have had one more for our atmospheres, but that's okay. Who cares? But yeah, 3 sig figs. We're good, and there's our answer. So we have gone to the beach with our 1.59 grams of chlorine gas in our mercury-filled tube, and then we've heated it up to 200 degrees and watched the pressure of the gas push down on the mercury and fun and blah, blah, blah. There we go. So, exciting. Here's another question for you. What would that height difference be if we were at a different temperature? Couple of ways we could approach this problem. But let's think about it. So, pH we can't really measure directly with this temperature. So pH is mercury, right? It's not necessarily the gas itself. So because it's mercury, we can't just say, okay, we're going to plug in our ideal gas law here and we're going to get pH directly. Not quite, right? Since mercury is not a gas. It's not going to follow these laws. We have a couple options, but let's hear your thoughts. What do you think we could do to solve this? We're gonna need to figure out the pressure of the gas. We have two options here. We could use either law. Because at this point we have already calculated our moles, we do know all four parts of that reaction. So we can just change the pressure or the temperature and figure out the pressure of the gas that way, since now we know how many moles we have. So with that number of moles, we can say, okay, now, volume's not changed, R is not changed, temperature has changed. We're going to put in our new temperature there and solve for the pressure that way. That would work. Or we could use the combined gas law, which I would think is probably a better idea. While the first one will work, it's one calculation, you're good to go, easy. However, that would, using the first one here, the first option, that would also make the assumption that we did not mess anything up in our first problem. So if we had calculated that number of moles wrong, and we then had used that moles to solve for the second part, we could potentially introduce some error there. So it's kind of depends on how much you trust yourself, right? However, second one will get you there, I think, a bit more easily. But let's go ahead and do both. Let's see if we can do both ways. It's a good exercise here. So for the the pressure of the gas would be nRT over V, right? If we were to solve the ideal gas law. We know we have that many moles. We have R. I'm not going to write the units for R, but same units as before. We now have 423.15. Oops, 625 liters. If we do this, we're going to get the pressure of the gas. And so we're going to be able to see what that height difference would be by subtracting our atmospheric pressure. But that's how we could solve for the pressure of the gas. The other way we could do it is use the relationship between pressure and temperature, right? We know that our combined gas law, we know that the volume is staying the same. If it's staying the same, we can just get rid of it. Who cares? Same thing on both sides of the equation. We could take our initial pressure, which was... where did it go? Over 473.15. And divide it instead by 423.15. We could solve for the pressure of the gas that way. The new pressure, that is. So it's up to you. It's both. You're both doing. It's one calculation, one step basically, for this. So theoretically, it's the same amount of work, but again, you're taking less of a risk by doing the second one. I think someone had asked that. So you would get. In this case, we're going to have atmospheres for the top one, and we're going to have millimeters of mercury for the bottom one. Or we could have used the atmospheres one, but since the height is going to be in millimeters of mercury, it's a little bit faster to do it this way. But yeah, we'll get that. So what's the pressure of the gas here? Let's see. 0.0225 times 0.08206 times 423.15 divided by 0.625. All right, so that I got was 1.25 atmospheres. And Kevin apparently has done this and got 880. Is that right? For the second one? Yeah, I got that for the second one. Okay, cool. Yeah, great. So these should be the same number. Let's just double check. Did we do something wrong? Let's find out. So I get 950 when I do this. So that tells us we've done something wrong somewhere in this mess of calculations. Unless I typed the number wrong. All right, let me calculate this again. So 0.0225 times 0.08206 times 423.15 divided by 0.625. Okay, I did get 1.25 there. So let's go check Kevin's work earlier. Just to be sure, 1.29 times 0.625 divided by 0.08206 divided by 473.15. Woohoo! I did get a different number, Kevin. I got 0.0207. Someone else do this calculation for me. Let's see who's right. So that's one way, by the way, that you can check your answers, because those pressures should be the same, right? We're not, both of these methods would work. So if you want to double check yourself and you have all this extra time to do so, it's one way to do it. All right, Tyler, bust out your iPhone. Let's do it. Good. Okay, with that, let me just see here. Okay, 423. Okay, that's better. Yeah, so, sorry, Kevin, you've been overruled. So let's adjust our answer earlier. What? That's not possible. I just calculated this and I got the same thing, and it worked with the bottom part. Aha! So both of you have typing problems. Okay, no, we're good. All right, if you do this, you will get 1.15 atmospheres. If you convert that, I think, let's see, times 760, I get 876.8 millimeters of mercury. And that's sufficiently close. So note that this is a little bit different than it should be because of rounding, right? So all the rounding that we did with our moles and all that stuff, that's where we're going to introduce a little bit of error. That, as you can see, it's 877 versus 880. It's close enough, right? Maybe. So that's why you should use the second method instead. So it eliminates that error from rounding and also eliminates the error that Kevin has typed in the wrong number. So there we go. We have proof now that for this type of problem, you'll want to use the combined gas law just to safeguard yourself against errors. Okay, let's adjust our mass, by the way. Let me fix that. 0.0208 times 70.9. Okay, it's 1.47. Okay, cool. So there we go. There's our proof, right? So if the pressure of the gas, let's say it's 880.1. Remember, that's pressure of the atmosphere plus the pressure of the height difference between them. So that's going to be 880 equals 760 plus the pressure difference. So pH would be 120.1 millimeters of mercury. Hooray! So, wow, we did a lot just for that. So there is your proof that the combined gas law is more appropriate for when things are changing than the ideal gas law is. An unexpected, but or rather it's, the meme, it's a surprise to be sure, but a welcome one, as it were. So there we go. Okay. Woo, that was exciting. Any questions on that monstrosity of a problem we did? I rather like having all this extra time. We can be pretty leisurely and do all sorts of crazy problems now towards the end of the semester. You all survived thermochem, so that's good. Okay. Alrighty then. Alrighty. So, it is time now for us to talk about the relationship between temperature and speed that we're going to see. So, suffice it to say that at a given temperature, whatever that temperature happens to be, this would be kind of our speed and then the just proportion of molecules. We're going to see that if you were to take a snapshot of the speeds of various molecules at a particular temperature, you would come up with a distribution like this. This is what's called a Boltzmann distribution. And so remembering that temperature is a measure of the average kinetic energy. So of a system, right? So you get one number for temperature. However, as we can see here, according to whatever experiment we've done, we see that we actually have gases of a whole bunch of different speeds happening here. We have some gas molecules or particles that are super fast, we have some that are super slow, and we have a bunch in the middle. And so our temperature will kind of tell us the average speed, which is going to be somewhere around here. Oh, that's a V. So your average speed is somewhere over there. If you were to just, like take all this stuff, you see the graph is kind of skewed a little bit towards the right. So we have some extra molecules that are going super fast. So that's going to skew our average just a little bit as well. We're going to have also here what's called the most probable speed. And of course, that's just going to be the top of the graph, right? Whichever one is if you were to just guess what the speed of a molecule would be, if you wanted to be following probability rules, you would guess that kind of top part of the graph. And we have another one called the root mean square, which takes into, it's basically the average kinetic energy of the molecules related to the speed. So we can kind of get three kind of bits off this graph. So let's look what happens when the temperature changes. We're going to do that in light blue. When we actually increase our temperature, we shift the graph over a little bit. So let's say that this was 300 Kelvin, and now we're at 400 Kelvin or something. We're actually going to shift our entire graph a little bit. And so we're going to see that all of those things that we saw before, we have kind of three speeds that we're interested in. We have the most probable speed. Let me write all these out, by the way. I guess I should do that. As I'm doing this, I want to say that people use U for speed for some reason instead of V. I'll have to double check. But for right now, we'll use V for speed, velocity, right? So we have the average speed as well, and then we have the root mean square, which is the average kinetic energy. Or it's the speed at the average kinetic energy. The RMS stands for root mean square. And so we can just basically compare these. We're always going to see the most probable will be the this will be the one on the left. This will be in the middle, and this is usually to the right. This is generally the case as we look at these speeds. You know what? Let me see if there's a nice graph. Mine's unfortunately it's going to be a total mess. So let's see. Boltzmann distribution temperature curve. Oh, thank goodness. Okay, there are pretty pictures here we can use. Okay, let's see. Oh, look, here's a lovely one. Okay, so let's, is this the right screen? No. How about this one? No. All right, let me write a new one. That's the one I want. Okay, so as we can see here, as we change the temperature of something, we shift our graph over a little bit. So you see it's still it's always skewed to the right a little bit, so we're still going to have these same patterns here. But we're going to see that, of course, the higher temperature we have a higher proportion at higher temperatures. You can see we have all sorts of different graphs showing exactly the same thing here. This almost looks like my writing. That's pretty funny. Oh no, I would never do a Z like that. Forget it, that's not mine. Okay, let's see if we can have... let's see if we can get root mean square in there. Okay, well, no, we have one here. Let's see if we can get one that has both of these things. Come on, graphs. Don't let us down. Come on, Google, you can do it. I want to find one that has a nice overlay, because this is just going to be super messy. No. Here we go. This is what I'm looking for. Okay, cool. I knew it. They were using U. Okay, we'll fix that. So notice here, temperature 2 is higher, right? We have shifted our graph to the right. We still have these 3 points we can talk about. We have our most probable, our average, and our root mean square. And so those points will also be shifted up accordingly based on the temperature. And so all of these will be proportional to the temperature change in Kelvin. As we can see here, the average in this case and the root mean, or the probable, are, that close. They're still that close in the new graph. The root mean square is a little bit further, and it's again a little bit further in the second one. So without having to completely destroy my lovely graphs, that's what we're looking at here. Okay, so switching back to our normal thing, these would all get shifted up at higher temperatures. Right? That makes sense, right? Temperature measures kinetic energy. Kinetic energy is related to speed. And so moving the temperature up increases all of these. Hooray. If you remember the kinetic energy formula from physics, we have two components to it, though. Kinetic energy is equal to 1/2 mv squared. So we've talked now about this speed component, or velocity, if you want to be in terms of physics. but this part we have not really talked about. And so if we want to think about it, we're going to see if things are going to have the same temperature, same kinetic energy, what do we think is going to happen if we change the identity of the gas? So we saw that, so this is essentially temperature, right? The kinetic energy measure is a measure of average kinetic energy. So if we just say temperature, which is wrong, but if we say temperature, we saw that as the temperature, okay, yeah, Kevin's got it. As the temperature went up, the speed went up as well. We're also going to see that if we make our mass go down, our speed will go up as well. And so we can see that, oh my goodness, there's such lovely graphs in this lovely Google for us. We can see here, look at these molecules here. We see we have hydrogen, helium, water, nitrogen, and oxygen. Hydrogen of all these will have the lowest molar mass. Helium would have the next lowest, followed by water, nitrogen, and oxygen. So as our molecule gets heavier in terms of molar mass, it's also going to get slower. So does that kind of make sense? Heavy stuff moves more slowly. We can apply that to, you know, a tractor versus, you know, a sports car or something. You know, lighter stuff moves more quickly. And lucky us, we have, so by the way, I have to switch all these to U's now because for whatever reason, again, we never like to have, you know, letters that make sense in chemistry. So while V would be nice for velocity, no, we're going to make it U for, I don't know what. I guess I have to switch all these as well. Here, I'll put little things on them. Now they're U's. Okay. So, looking at this, we're going to see the root mean square I think it's, yes, where M is your molar mass. Fancy M. Oops. So let's take a look at this. We're going to compare gas speeds of different molecules. On Monday, by the way, just so we know what we're doing. So I am, in this chapter, I do teach things a little bit differently than the order that's presented in the book. So we're going to talk about partial pressures and that sort of thing a little bit on Monday instead. Mixtures of gases in that way. But right now I wanted to talk about speed, because why not? So for, let's say, let's see what the root mean square speed. Yes, it is the same constant as before. I hope. No, it should be. Yeah, why would it not be? Alrighty, so let's go ahead and see what we can do here. Temperatures, I think it is already in Kelvin. And then we have our molar mass, which is going to be 32 grams per mole. So you might be thinking, okay, the units of R here are going to be a little bit strange. We may need to adjust our R to accommodate these units. I'm trying to think what... in atmosphere is in SI units. Let's just find out R in SI units. So this is joule per mole Kelvin. Yeah, I don't care about that. I want, fine, what is a joule in SI units? Okay, so it's a newt. Okay, let's just say base units. Sorry, this is stuff that I totally don't remember. Okay, joule is kilogram meter squared per second squared. Okay. Oh, but what's a liter times an atmosphere? Ah, sorry guys. This is so annoying. All right, well, let's do it this way. So it is the same gas law, but we may need to adjust the units here so that we can cancel out our grams that we're going to deal with here so that we can actually get a speed unit out. So let's go ahead and look at that. So 0.08206. Always Tyler is messing me up here. Okay, so that's, we have our units there. So we have liters atmospheres per Kelvin mole. That's the same thing as 8.31 joules per Kelvin mole. A joule is equal to a kilogram times meters squared per second squared. Or is it a kilogram meter? My God, I'm so sorry. I'm so bad at these base units. Okay, it is kilogram meter squared per second squared. Okay. Thank goodness. Oh my gosh, and I'm totally out of room. Second squared, Kelvin, mole. Those are our units on the bottom. All right, now let's see if we can get all this stuff to work out. So it looks like we have our grams thing is not going to work out nicely for us. So we're going to want to adjust our R accordingly. Grams times meters squared per second squared times Kelvin times mole. Okay, are you happy now, Tyler? So it is indeed the same concept, but now I've thrown some other units in there. Okay. So with all this craziness now, actually, thank you, though, because I had forgotten that we did need to change the units for that. So, and then 32 grams per mole. Okay, we finally have our things in the units that we want. So, kelvins cancel, moles cancel, grams cancel. Hooray! At least that part we have now. So we're left with meters squared per second squared. And notice that if we do a radical of that, we're going to get meters per second, which lo and behold, that is our magic, speed unit, right? Meters per second is a speed unit. So let's go ahead and now calculate this, if someone would be so kind. You know what? I don't trust you guys anymore. I'll have to do it myself. Okay. Actually, no, that seems very reasonable. But just to be sure, 8314 times 300 divided by 32 to the 1/2 power. Kevin, I seem to have gotten a different answer than you. I got 279. Did I copy it wrong? 8314, 300, 32. All square rooted. Kept the oh, there's a 3 there. Very good, Kevin. Whoops. I forgot we have a 3 in the equation. Kevin has outsmarted me today, everyone. I forgot the 3. My bad. All right, Kevin, you have redeemed yourself. Oh, I got 484 as well. Awesome, awesome, awesome. Aren't these calculations so fun? Nobody can do them right. Okay, so we're going to see that our oxygen molecule will have a root mean square speed of 484 meters per second. How exciting. Let's do it for one more gas. How about for HCl? Thankfully, we can keep all of this crap the same. And then we just need to change our molar mass, which is for HCl is going to be what, 36.46, I guess. It's easier when we already have this stuff. All right, so I'm just swapping out 32 with 36.46. Doing that, we get 453. Actually, that'll be fine. Meters per second. So notice, oxygen gas is smaller, it has a lower molar mass, will be moving faster, right? Molar mass is in the bottom of our equation, wherever our equation went, all the way up there. So the lighter stuff should move more quickly. We have a way of talking about this, thankfully. We can compare two of these in one step, because they're all going to have this 3RT thing as part of their formula. We can just, condense it. If we wanted to compare these two, we could just rearrange the equation like this, where we'll have the speed of whatever gas we're looking at, speed of another gas, molar mass of the second gas over molar mass of the first gas. Since 3R and T would be the same, since the gas would be at the same temperature, R is a constant, and 3 is a constant. So we can use this to compare speeds of something. So we should see, here's our big check here, we should see that 484 over 453 should be equal to radical 36.46 over 32. Let's see if we're right. This is always exciting because I don't know when I just make up these problems if it's gonna come out nicely. So this is 1.068. And let's see, 36.46 divided by 32. Square root that. Please work. Oh my goodness. Okay, it's slightly off because we've done some rounding, but hooray! We have done it. It checks out. So this tells us, by the way, if we were to say in words, at least the root mean square speed. You could use this for any of them. You could use this for most probable. You could use this for average speed, whatever. It'll work for all of these. So, but for this particular one, we're showing that the oxygen is a little bit more than 1 times fast. It's a little bit faster than HCl is because its molar mass is a little bit lower. This is something called Graham's law, by the way. We'll give some credit there. You don't need to memorize the name. Graham's law is officially this one, by the way, up here. But again, you do not need to learn the name of this. So just understand this is yet another one of our gas laws. So this would be comparing speeds based on their molar masses. All right. Sorry for the unit snafu there, but we figured it out. And we all did it together. Isn't that exciting? Actually, this feels very much like that time I came up with the equation that was such a pain in the ass to balance. That I took like 5 minutes to do it. Yikes. But whatever, it's fun. Yay, teamwork. Alrighty, I guess before I go, I should just remind you guys, I did send out an email yesterday about students who may be considering dropping. Just to reiterate, you should check that email if you haven't already. A couple things to consider in there. Just remember the drop deadline is Friday. So if you are planning to drop, make sure you do it by then. Otherwise, you'll be stuck with me, and then we'll be fun. We'll have another month of fun together. So, if that's something you want to do. So, alrighty. With that, I think tomorrow. Wait, are we doing class tomorrow? No, I don't think we need to. I mean, we're totally fine in terms of our pacing of this course already. So, someone remind if I did say we're doing Thursday. I don't think we are. So I'll probably see you Monday. Though if I am wrong and I did say I was gonna do Thursday, we can do that. But for right now, I think we're just gonna meet back on Monday. So I'll put up some homework for this so you guys can get started. We're not done with this chapter. We're gonna still have more. Actually, no, you already have homework, right? You're working on your 8 and 9 homework right now, or 7 and 8, whatever the chapters were. Focus on that right now. Let's not work. I'll put the gases homework up, but it's going to be due next Sunday. Okay, so you can start working on it if you want, but right now focus on the ones that are coming up due this weekend. Okay, awesome. Well, with that, I'll see you guys on Monday.